And that's the last one. Finally, I finished my humane open field sheep farm.
Now, the obvious question that all farmers ask after doing this is, what is the frequency of specific genetic traits in this population? On the AP Biology exam, you might be asked to predict these frequencies of a given population. To determine this frequency, we use what is known as the hardy-weinberg equation. This is a mathematical equation used to illustrate the relationship between all genotypes present in the population in question. Speaking of genotypes, we should know the difference between a phenotype and a genotype to begin this. A phenotype is a visible, outward appearing characteristic, such as this rabbit with brown fur. A genotype, on the other hand, is the genetic basis of that physical characteristic. For our brown fur example, the specific combination of dominant and recessive alleles that is expressed as either brown fur or non-brown fur would be considered the genotype. In general, there are three different kinds of genotypes: homozygous dominant, homozygous recessive, and heterozygous. Homo meaning the same and hetero meaning different. In our scenario, we'll be using the color of the sheep's wool to determine frequency. Red is dominant and blue is recessive. Homozygous dominant would be capital T, capital T. Homozygous recessive is lowercase t, lowercase t. And heterozygous is capital T, lowercase t. The T stands for sheep color. See? It's right there. To sheep color. Now, getting started with the actual equations. There are two of them that you need to keep in mind. The first one is P plus Q is equal to 1. P stands for the dominant allele, and Q stands for recessive. If there are 30 sheep and all of them are homozygous, then we just count the 10 blue sheep there and we find out that Q is equal to 10 over 30. As a decimal, it's 0.3333333333333333333.
Let's just round it to 0.33. Now, using basic algebra knowledge, we subtract 0.33 from 1 and find that our P is equal to 0.67. Our completed equation is 0.67 plus 0.33 is equal to 1. We now know that 33% of the sheep population has blue wool and 67% has red wool. Yay, math! But often, that equation is used as a tool to find the answer to our second equation. Our second equation is P squared plus 2PQ plus Q squared is equal to 1. It looks complicated. I promise it isn't. We can visualize it with a Punnett square. That's the famous biology saying, all roads lead to Rome, Punnett squares. If we just put P and Q up here, and then P and Q on the side, we see that in this box it's PP. PP. P multiplied by itself is P squared. In these two boxes, we see PQ. Add them together, and you get 2PQ. In the final box, similar to the first one, you get QQ or Q squared. The P squared stands for homozygous dominant, 2PQ stands for heterozygous, and Q squared stands for homozygous recessive. We can finally get to the example problem. 60% of these sheep are blue. You know this because I gave you the number. I know this because I kept falling asleep while trying to count them. It took me months. Because red is a dominant trait, this means only sheep with a homozygous recessive genotype will be blue. Therefore, our homozygous recessive frequency, or our Q squared, is 0.6. Our question is, how can we determine the frequency of the heterozygous genotype in the sheep population? First, we start with the basic Hardy-Weinberg equation, adding in our known Q squared value of 0.6. Next, we determine the value of Q by taking the square root of Q squared. The square root of 0.6 is 0.77. This means that Q is equal to 0.77. Using the knowledge of P plus Q equaling 1, we can solve for P. 1 minus 0.77 is equal to 0.23. So, our P value is 0.23. We now have all the knowledge we need to solve for the frequency of the heterozygous genotype, which is represented by 2PQ in our Hardy-Weinberg equation. Since we know the values of P and Q, we can calculate the frequency of this genotype. 2 multiplied by 0.23 multiplied by 0.77, this comes out to 0.35. The frequency of the heterozygous genotype for a red or blue sheep is 0.35 or 35%. Phew, that was a lot of work. I sure hope nothing happens that would change the frequency of this population's making me do the calculations again.